All right, today we're diving deep. We are heading to the very edge of what we know to talk about one of the most mind-bending ideas in all of science. The fact that our entire universe is getting bigger every single second.
And you know, Richard Dawkins really nailed it with this quote. The concepts we're about to get into are going to challenge your intuition about space and time and even where we fit into it all. It's a wild ride.
So, this is the big one, right? The question everyone asks, if the whole universe is expanding, what's it expanding into? It feels like a total paradox. But hang with me. To even begin to answer that, we have to build a basic model of what the universe is actually like. So how do you even start to describe the entire universe? It seems impossible. Well, scientists begin with one really powerful, really simple assumption. It's a principle that basically underpins all of modern cosmology, and it lets us create one single picture of, well, everything.
This big idea is called the cosmological principle. It basically says two things. First, if you zoom way, way out, the universe looks pretty much the same everywhere. And second, the laws of physics that work here on Earth, they work the same way everywhere else too. In other words, there's nothing special about our little corner of the cosmos.
And you can actually see it. When we point a telescope like the Hubble at a seemingly empty patch of sky and just let it stare, this is what we get. Every single one of those little specks is an entire galaxy. And look at them. They're scattered pretty evenly all over the place. This tells us our assumption is solid, and that lets us build one model for the whole shebang.
Okay, so if the universe is uniform, what does that actually mean for its overall structure? I mean, what's its shape? Well, according to Einstein's theory of general relativity, a universe like ours can only have one of three possible shapes, or what physicists call geometries. So this slide lays out the three big possibilities. The first one is a flat universe. It's the one that feels most normal to us, like a giant, infinite sheet of paper. Then you have a closed universe, which is like the surface of a sphere. If you started walking in a straight line, you'd eventually end up right back where you started. And finally, there's the open universe, which is shaped like a saddle. In that universe, two parallel lines would actually curve away from each other over time. The very rules of geometry change depending on the shape of space itself. So we've got a uniform model and three possible shapes. But how do we know it's actually expanding? This isn't just some cool theory. This is based on real-world observation, the smoking gun of cosmology. It all comes down to light. So a distant galaxy sends out light, and that light travels for billions of years to get to us. But while it's traveling, the actual fabric of space between us and that galaxy is stretching. Now this is the really key part. The galaxy isn't just flying away from us through space. Space itself is expanding, and it literally grabs that light wave and stretches it out along for the ride.
And we call this effect redshift, because stretching a light wave makes it look redder to us. It's a direct measurement of how much the universe has expanded since that light first left its home galaxy. So the bigger the redshift we measure, the farther away that galaxy is, and the more the universe has grown in the meantime.
Okay, so redshift tells us how much space has stretched. Got it. But to really map out the expansion, we need the other piece of the puzzle. How in the world do we know the actual distance to these galaxies that are billions of light years away? Well, astronomers have a really clever trick for this called a standard candle. Just imagine you're in a dark field and you see a light bulb. Is it a dim bulb up close or a really bright bulb far away? You can't tell, but what if you knew it was a 100-watt bulb? Then you could tell its distance just by how dim it appears. Astronomers do the exact same thing, just with special stars. And here are our two favorite cosmic light bulbs. Cepheid variables are these amazing pulsating stars that Edwin Hubble first used to measure galaxies nearby. But for the really, really distant stuff, we use Type 1a supernovae. These are exploding stars, and they are so incredibly bright and so consistent that we can use them as perfect standard candles all the way across the observable universe. They are the gold standard.
So now we have our tools. We've got redshift to measure expansion, and we've got standard candles to measure distance. All it took was for one astronomer back in the 1920s to put those two things together and change our view of everything.
Working at the Mount Wilson Observatory, a man named Edwin Hubble painstakingly measured the distances and redshifts for all the galaxies he could see. And when he put all that data on a graph, he found a pattern. Not just any pattern, a clear, simple, and absolutely world-changing relationship.
And this is basically what he saw. The relationship was just simple. The farther away a galaxy was, the faster it seemed to be moving away from us. A galaxy twice as far away was moving twice as fast. 3 times as far, you guessed it, 3 times as fast. It was a perfect straight line.
This beautiful linear relationship is now known as Hubble's law. It's one of the cornerstones of cosmology. It's that simple little equation. A galaxy's velocity equals its distance times a special number we call the Hubble constant.
So what is that number? What's the rate of expansion? Well, our best modern measurements put the Hubble constant at about 73 kilometers per second per megaparsec. Now, a megaparsec is just a huge unit of distance, about 3.26 million light-years. So all that number means is, for every 3.26 million light-years farther out you look, the universe is expanding 73 kilometers per second faster.
This law is the ultimate proof, the smoking gun that the universe is expanding. And the implication is profound. It means we aren't at the center of some cosmic explosion. Because space everywhere is stretching uniformly, an observer in any galaxy would see the exact same thing, everything moving away from them.
Which brings us all the way back to our first big question. What is the universe expanding into? The answer is nothing. Think about the surface of a balloon as you blow it up. For a tiny ant living on that surface, its 2D universe is getting bigger, but it's not expanding into anything in its 2 dimensions. Our 3-dimensional space is doing the same thing. Space itself is what's expanding.
So we figured it out. The universe is expanding. But the story gets even weirder. In the late 1990s, astronomers using those Type A supernovae, our standard candles, found something that nobody expected. Not only is the universe expanding, but that expansion is accelerating. It's actually speeding up. And figuring out why, well, that's the next great cosmic mystery.